Hello, everyone. Welcome back to another Flan Talk. Today, we're excited to have Grigoris Velegkas. He recently graduated from Yale and is currently a researcher at Google Research. And today, he's going to give us some interesting perspectives on language models. So, thanks, Grigoris, and take it off.
Hi everyone. Thank you very much for having me and for joining the talk. I'm going to talk to you about language identification, generation, and hallucination detection in the limit. This is based on joint works with a bunch of folks from Yale. And it would be great if we can make the talk a bit interactive. So at any point, if you have any questions or if anything is not clear, please feel free to stop me and we can clarify things. Okay, so computer scientists have been very excited and fascinated by the phenomenon of language acquisition by both humans and machines and have been trying to come up with models to understand that for many decades. This has started from the work of Shannon back in the 60s, then moved on to Chomsky, who defined the hierarchy of formal languages. And most recently, there has been a ton of applied work that has culminated in LLMs that have had amazing performance in very many different tasks the past few years. Okay, so let's try here to take a step back and let's try to understand what is the problem that the LLMs are trying to solve. So very abstractly, the LLMs collect a very large collection of data in the form of text mostly, and they're trained on them. What they do afterwards is that, given some prompt, they assign probabilities to every possible continuation of the prompt, every possible sequence of words. And what they do is that they produce strings which have a high assigned probability. So at a high level of abstraction, one could say that this is roughly what's going on with LLMs. But now, in some sense, assigning probabilities to this generation problem was our decision. Like we didn't have to work with probabilities. So Kleinberg and Mulanathan decided to strip away the probabilities from that setting and abstract the problem and simplify it a bit further. So what they said is that perhaps the simplest problem statement that one can come up with about what the LLMs are doing is that given a corpus of data from some unknown language, they want to produce valid unseen strings from this underlying language. And just to give some toy running example to have in mind, we can think of strings as a sequence of symbols of the English language. And the underlying true language that the LLMs are trained on are all the correct C programs, for example. Okay, so the the goal of Kleinberg and Glanathan was to come up with a theoretical model which captures this problem. And what they did was that they started from this very influential paper by Mark Gold, who proposed the setting of language identification in the limit. This paper contained a lot of pioneering ideas. For example, Mark Gold was saying that he wanted to construct a precise model for what it means to be able to speak English in order to understand theoretically what can be achieved by these artificial agents. And he also mentioned that since it's hard to explicitly write down the rules of the English language, this artificial intelligence agents will have to learn implicitly how to do that by using data. So in this setting of language identification in the limit, what was proposed by Gold in 1967 and further studied and fully characterized by Dan Anglin later on, we define language identification as a game between an adversary and an algorithm. So what the adversary does is that it thinks of some target language K, which comes from a non-countable list of such languages. For example, it could come from the list of all regular languages, the list of all context-free grammar, so on and so forth. And now in every round, the adversary enumerates the strings of this language K to the algorithm one by one. And this order of the enumeration is not fixed, but it's rather chosen by the adversary. After the algorithm sees one of these enumerated strings, its task is to output its guess, some index, some natural number, and this natural number corresponds to what the target language is. So its goal is to be able to figure out what is the index of the collection, which corresponds to the language that the adversary had in mind. And in this setting, we say that the algorithm succeeds in identifying k in the limit if there exists some number t star such that for every time step t after t star, the algorithm guesses the correct language. Okay, so one thing that I want to mention here is that there are a bunch of things going on. There is some target language K that the adversary is choosing. There is some countable collection. There is also some arbitrary enumeration. This T star is allowed to depend on all of these things. So it's truly something that happens in the limit. Is the setting clear? Okay. Okay. So a bit more pictorially, what's going on is the following interaction. The adversary on the left reveals a string of the hidden language K to the learner, and then the learner on the right comes back and says what is its guess for the index of the underlying language K. And this goes on forever. Some important things that I would like to point out here is that the algorithm never sends strings that are not in the target language K. In other words, the algorithm only receives positive examples containing elements of the language. The algorithm is never told whether its guess is correct or not. Um, and lastly, and importantly, the algorithm cannot ask the adversary if a string of its choice is in the target language. So in the most basic version of this setting, the algorithm does not have this type of access to the target. Okay, so now one theorem that was shown by Gold in this paper, informally, is that language identification in the limit is impossible even for simple collections such as all regular languages. And later on, in these two papers, Dean Anglin fully characterized which collections of languages allow for identification in the limit in this setting. And I will have the precise condition later on in the talk. Okay, so let's take a step back here. We said that the problem formulation that we have in mind for LLMs is that given strings from an unknown language, we want them to produce valid unseen strings from this language. Gold asked for something which seems to be harder. He asked for algorithms which given strings from an unknown language, need to figure out exactly what is this language. So building on this framework of Gold, let's see how Kleinberg and Mulanathan defined the easier setting of language generation in the limit. So now we have a new game. Again, we have an adversary and an algorithm. The adversary's job is pretty similar to what was happening before, as at the beginning, the adversary thinks of this secret target language K from the countable list. and starts enumerating the strings of the language one by one. Just to set up a little bit of notation here, we will denote by S sub t the set of strings that have been enumerated by the adversary up to time step t. Okay, so we said we have a new goal for the algorithm. What is the new goal? Now the algorithm at any time step t, instead of trying to figure out what is the index of the target language, it only has to figure out a new unseen string that does not belong to the language. So from that formulation, we can see that language identification always implies generation in the limit, with one caveat. We asked that the algorithm has to keep on guessing new elements from K. So we have to ensure that there are sufficient elements from K so that this can happen. And for that, we restrict ourselves to collections where every target language has infinitely many elements. This is not a very big deal, and this is not what's driving the results. We're not making the setting easier by doing that. Just like something to keep in mind. Since we require that the algorithm keeps on figuring out new elements of K, we need to ensure that K is infinite. Okay, is the new setting clear and how it differs from the previous one? Okay. Okay, so again, pictorially, the only thing that changes is the algorithm's responses. The adversary thinks of the target language K, starts revealing strings of it, and then the algorithm, instead of guessing the index of the target, it guesses a new unseen string from the target K. Similarly as before, the algorithm never sees negative examples. It never receives any type of feedback about how the strings that it generates look like, whether they are indeed part of the language or not. And as I mentioned, one thing to keep in mind is that for this setting, we need to assume that all languages are infinite. Otherwise, the generator might trivially fail because it will run out of elements to generate. Okay, so now in stark contrast to the setting of language identification in the limit, in this setting of language generation in the limit, Kleinberg and Planathan in last year's NeurIPS showed that language generation in the limit is possible for any countable collection of languages. So on the one hand, for identification, we know that this is a very hard task and a very limited set of languages allow for that. On the other hand, generation is a much, much easier task, and it turns out that it's possible for any countable collection of languages. And in this like a running toy example that we have in mind about C programs, in both generation and identification, after the algorithm has seen finitely many C programs, generation tasks requires that the algorithm is able to out-valid unseen string C programs, whereas identification requires that at some point the algorithm is able to spit out some valid grammar for C. And from that, we can see that perhaps we expect that generation is easier than identification, but before Kleinberg and Vlanathan's result, it was not clear how big the gap is. Any questions here? Okay. Okay, so something to keep in mind here is that in this specification by Kleinberg and Mulanathan, the algorithm only needs to be able to generate from an infinite subset of K. So there seems to be some ongoing tension between validity, meaning that the algorithm only generates valid strings from the target language K, and breadth, which is trying to capture how big of a subset of the target the algorithm can generate from. And this is something that I will get to soon in the talk. Yeah, and like in a more applied setting, this can also be called as hallucination versus mode collapse trade-off. Okay, so just to give you a sense of why language identification is very hard, let's consider the following setting. Imagine that the domain, the set of strings that the algorithm sees, is the set of all integers. And let's define the language li to be a threshold centered at the integer negative I. Now, here I runs from 0 to infinity through all the naturals. And we also define a special language, which we denote by L infinity, which is just the set of all integers. Okay, so let's see here how the adversary can fool the identifying algorithm, no matter how the identifying algorithm behaves. So we start with the language L0. And now what the adversary does is that it starts enumerating the elements 0, 1, 2, 3, 4, so on and so forth. And basically, there are two possible scenarios that we care about. Either the algorithm will never say that the target is L0, in which case the adversary has produced a valid enumeration for L0 and the algorithm has never figured out what is the correct index. Or at some finite time step t, the algorithm will say that, okay, I believe that the target language is L0. Okay, assuming now that we are in the second scenario, because in the first scenario the algorithm has already lost, let's now imagine that we're in the second scenario. The moment that the algorithm says L0, what the adversary does is that it enumerates the element -1. So, continuing in this fashion, the algorithm is again cornered. Either it will never say L1, so it loses, or at some point it will say L1, in which case the adversary again moves on to enumerating L2. So going on in this with this diagonalization type of argument, we can see that either at some point the adversary will stop at some language li and the algorithm will lose, or the adversary will keep on going on and enumerate the whole infinite set of integers, so the algorithm will make infinitely many mistakes. So this is like some example to have in mind about like why identification in the limit is hard. Is the construction here clear? Okay, so okay, having seen that, maybe let's try to come up with some attempt about how one could try to show the theorem that Kleinberg and Planathan proved. And we will start with a proof strategy, which is wrong and is doomed to fail, but it will be instructive in order to understand their algorithm better. So, since the collection is countable, we will write the languages down one by one, L1, L2, L3, L4, so on and so forth. So now, let's think about the following idea, which turns out to be wrong. If at any given point, what we will do at any given point is that we will guess the index of the language, which is consistent with the enumeration we have seen so far. So if L1 is the first consistent language with everything we have seen so far, we will guess L1. If at some point L1 is contradicted by the input stream, we will move on to the next one, so on and so forth. And now this like a wrong proof idea is that since the target language is equal to LZ for some target Z, we will eventually get to this language K by moving on from all the previous languages. And after that, we will never move beyond K. Okay, unfortunately, this idea fails, and one easy reason to see why it fails is that it would also give us language identification in the limit, which we know is not possible. But let's try to understand why. So imagine that we are in this setting here. We say, and the target that the adversary chooses is L6. Now, we say that some language li is consistent at a time step t if all the strings that the adversary has enumerated so far are a subset of this language. Okay, so let's start with L1. This is the first language in the collection, so this is the first possible guess we might make. Now, in the first round, assume that the adversary enumerates this element over here, the white one. White cells here means that this element does not appear in the language, whereas green cells mean that this element does appear in the language. So after the adversary enumerates this guy here, the algorithm will figure out that L1 is contradicted and it will move on to L2. So in the next round, the adversary enumerates an element of L2, so the adversary remains there, so the algorithm remains there. And then in the next round, the adversary enumerates this element here. So the algorithm moves on from L3 and goes all the way, goes all the way to L4. So what will happen at this point is that L4 is a superset of L6. So no matter what the adversary enumerates, the algorithm will get stuck there. So the main pathology of this algorithm is that it can never move on from supersets of the target. If there's a superset somewhere in the collection coming before the target, the algorithm will not be able to figure it out and it will get stuck. Okay, is this clear? Okay, sounds good. So now let me move on to the actual correct algorithm that Kleinberg and Vlanathan proposed. In order to do that, one definition would be very important, and this is the definition of the so-called critical languages. We say that a language L sub n is critical at some time step t if two things happen. First of all, this language needs to be consistent with the input. If the language is not consistent, there's no reason to consider it. And secondly, if some language li that comes before L sub n is consistent, then L sub n needs to be a subset of li. So pictorially, these critical languages form some chains of inclusions. And two facts are important. The first fact, which is perhaps easier to see, is that critical languages do exist. In particular, the lowest indexed consistent language is a critical language. And secondly, which is the main ingredient that is used in the proof, and I will not have time to give the formal proof of that, is that the target language will eventually become critical, no matter what this target is, and no matter what enumeration the adversary gives to the algorithm. Okay, so now, how does the algorithm use these critical languages to generate in the limit? So at any given step, the algorithm only considers the first t many languages, L1 through LT. And what it does is that it finds the critical language with the highest index that is less than t. And let's denote this language by L sub nt. So once the algorithm has identified this language, what it does is that it simply generates an unseen string from it. Does the algorithm make sense? So again, we just consider a prefix of the collection. And what we do is that we find the critical language with the highest index among that prefix. and then we just generate a new string from it. Okay, so given the previous two ideas that I mentioned, the proof works as follows. For a large enough times, sorry, was there a question?
Yeah, sorry, I have
Yeah,
a quick question.
yeah, yeah.
How do you, is it easy to actually identify the critical language within the, how do you do
Uh,
that? How does the algorithm identify the critical language with the critical language with the highest index?
yeah, so for that, we assume that the algorithm has access to a subset oracle, which can take any two languages of the collection and ask whether this language, one language is a subset of the other.
Okay,
So
okay,
we have two oracles. One is the membership oracle, which takes any string and any language and
hmm,
asks if the string is in the language, and the subset oracle.
okay, I see.
One thing that, yeah, thanks for the question. One thing that I want to point out is that there's a more convoluted version of the algorithm, which works with membership oracles only. So this definition of critical language is useful, but we can work with weaker oracles as well. We don't have to have the full power of this subset oracle. Okay, and now like the proof idea is that for a large enough time step t, the critical language the target language will become critical and will be a part of this prefix L1 through LT. And by this subset property that critical languages have to satisfy, the critical language with the highest index, L sub NT, will be a subset of LZ when this happens. So any unseen string from L sub NT is also an unseen string from LZ. So the main idea that goes into the proof is showing that LZ will indeed become critical at some point. Okay, so modulo this part, which I'm not able to prove in the talk. Is there any question about how the algorithm works? Okay, so maybe I will move on. So pictorially, the critical languages look as follows. The first critical language is Li1. The second critical language, Li2, is a subset of Li1, so on and so forth. At some point, we hit K. K is the target that the adversary has in mind. And what happens from this point on is that this prefix of the chain will stabilize throughout all the interaction. And then everything that starts after K will keep on getting contradicted because these guys are subsets of K. So eventually we will see something that does not belong to them. So they will get contradicted, and then new chains will start emanating from K. And this thing will go on forever. So this is roughly like how the pictorially how the Kleinberg-Muller-Nathan algorithm looks like. Okay, so now I want to mention a bit more formally this validity versus breadth trade-off. As we saw before, this algorithm generates from a continuously decreasing subset of K in order to achieve correctness. And the main question that Kleinberg and Glanathan asked is whether this is necessary. Since then, there have been a bunch of follow-up work studying this problem. And I want to advertise here that if you're interested in this setting and in this direction in general, Moses Tsarikar, Chirag Paparazou, Anna Imerotra, Charlotte Pill and I put together a tutorial at last year's Cold, which you can find on this website along with other related material. So yeah, if you're interested, please visit this website. Okay, so in order to study this validity versus breadth trade-off, it is important to have a more formal notion of what breadth is. So now I want you to change the viewpoint of what the algorithm does. And instead of imagining that it outputs one element at a time, let's imagine that it outputs a whole set, a bunch of elements at every time step. So like in this toy example here, the green circle denotes the target language K, the purple circle denotes the training data, and the yellow one denotes the elements that the generator is outputting. And as we can see here, this generator has more and more breadth as time goes on. So this is intuitively what we would like to capture with the notion of breadth. Okay, and why is breadth important? It is important because it captures which part of the target language the generator knows. And it's also important because users are asking a bunch of weird questions, like drawing a panda surfing in a watermelon juice with sunglasses while sinking, or like solving new and unseen math problems. Yeah. And with that, I would like to mention that even though the setting that I have explained to you so far is promptless, it does not allow for the user to give a prompt to the model or anything like that. Kleinberg and Planathan showed that a natural extension of the model, which allows for prompts, has all these properties that I described. So this is almost without loss of generality, not allowing for prompts in this setting. Okay, so with that, let me make the definitions of breadth that I will explain here a bit more formal. So we have two notions of breadth. The first one is called exact breadth, and is basically almost the same as identification in the limit, where we are asking for the generator to be able to output all the unseen part of the target language K. So again, K is this like green circle, and then the output of the generator needs to be able to capture all the unseen part of the green circle. And we also have a notion which we call approximate breadth, where we relax the requirement a little bit, and instead of asking that the generator captures the whole part of K, we allow the generator to miss finitely many elements of it. But we're still asking that the generator is a subset of K. Okay, do these two things make sense? Okay. And again, just to give you a toy example, imagine that the target language is the set of all natural numbers. One generator is a threshold centered at the natural number I. So this generator does not have exact breadth, but it has approximate breadth since it only misses the first I minus one elements of K. And the second generator might be the set of all even numbers. This generator has neither exact breadth nor approximate breadth because it misses infinitely many elements of K. So between the first one and the second one, perhaps we would prefer the first one, which only misses finitely many elements. Okay, we can also, we have considered way more definitions, both in our paper and in some other works, which I won't have time to get into. I just wanted to give you a sense of what one can ask for here. The main results that these two works showed is that for any language collection L, a generator can generate L with exact breadth if and only if L is identifiable in the limit. And second one is that a generator can generate L with approximate breadth if and only if L is almost identifiable in the limit. And I won't have time to define what this almost identifiable here means, but I will try to explain it by showing you what is the characterizing condition for this setting and how it can be modified to give a characterizing condition for that setting. Okay, and what is the proof strategy for these ideas here? We again do something like diagonalization, as I showed in the previous example, which shows that a certain collection of languages is not identifiable in the limit. Okay, and moreover, we throughout this talk, we have been working in a setting which does not have any distributions. What we showed is that basically these results go through in a natural setting where the samples are generated from an adversarially chosen distribution and not from an adversarial enumeration. Okay, so what does this condition of identification look like? In case you are familiar with VC dimension, Littlestone dimension, and these things, you will notice that this characterizing condition, which was identified by Dane Anglin in the 80s, looks significantly different from that. So this condition says that any collection of languages, script L, is identifiable in the limit if and only if every language L has a finite telltale subset, which means that for any language L prime, if this telltale subset belongs to L prime, then L prime is not a proper subset of L. Okay, so perhaps this is kind of hard to grasp on the fly, so let's see a pictorial example. Imagine that we have this language cell in blue shade here, and let's assume that this purple circle is a telltale for L. So a telltale, again, needs to be a finite subset of L. So all good so far. Imagine that the TL is finite, and we can also say that it is a subset. Okay, so now what cannot happen is that there cannot be another language L prime for which TL is also a subset, and L prime is also a proper subset of L. So the Dane-Anglin's condition basically uh, takes away all these pathological examples from the collection. And the very nice thing is that this is precisely what characterizes identification in the limit and has connections to breadth, as I said before. Okay, so uh, perhaps it's easier to think about the negation of this condition. So, what happens is that if this collection is not identifiable in the limit, it means that there exists some bad L star that does not have a telltale. So this says that for every finite T, which is a subset of L star, this purple circle here, there exists some other language in the collection L such that T is both a subset of L and L is a proper subset of L star. And just to give you a hint about these proofs, we use L star to do diagonalization whenever the collection does not satisfy this condition. Okay, so is the is this picture clear about um, what is the object that makes identification hard? Okay. Okay, so having explained this setting of both language identification and the limit and language generation and the limit, I want to move on to the last part of the talk for the next few minutes and describe a formal setting of hallucination detection in the limit based on these ideas. Okay, so let's try to formalize the problem of hallucination detection using similar vocabulary as we have been using throughout the talk. So we model the ground truth as some language K, which is a subset of a domain X. So this means that whatever is in the target language K is correct, is true in this world, and whatever is outside of K is a hallucination, is incorrect. So for our definition, hallucination has a binary flavor. And now we model the LLM as some other language C, which is a potentially different subset of the domain X. And under this formulation, the we say that the LLM hallucinates if this subset of the domain G is not a subset of K. So if G contains elements outside of K, we say that the LLM hallucinates. Otherwise, we say that the LLM does not hallucinate. So again, the definition has a binary flavor. If if the LLM contains even a single element outside of K, we say that it hallucinates. Otherwise, we say that it does not. Okay, and now let's define the hallucination detection game, which will be again a game between an adversary and an algorithm. So here, the job of the adversary is slightly different. The adversary not only thinks of a target language K from this countable list of languages, but also it picks a target set G, which should be thought of as the target LLM. And this target set, G, does not have to be part of the countable list. It can be any set of its choice, as long as it's a subset of the domain X. Okay, so again, similarly as before, the adversary enumerates strings of K one by one. The adversary still does not reveal what the target K is to the algorithm. But compared to what was happening before, we augment the algorithm with query access to G. So the algorithm cannot does not have query access to K, but it does have query access to G. And the reason why we do that is that many LLMs these days give access to log probabilities and these things, so it's much more reasonable to assume that one can get query access to the LLM rather than get query access to the target language. Okay, and now what the algorithm does is that in every time step t, it guesses a binary signal basically. And this guess corresponds to whether the LLM is a subset of K or not. So if the algorithm thinks that the LLM is not a subset of K, it outputs 0. If it thinks that the LLM is a subset of K, which means that it does not hallucinate, it outputs 1. So 1 means no hallucination, 0 means hallucination. Okay, and now we say that the algorithm succeeds in this game if its guess is correct after some finite time step t star. And again, like similarly as in all these previous models, T star is allowed to depend both on the collection, the target, both the target language and the target LLM, as well as the enumeration that the adversary gives. Okay, so similarly as before, the algorithm never sees strings not in K, the algorithm is never told whether its guess is correct or not, and it does not have query access to K. So our main result shows that hallucination detection in the limit is possible if and only if K comes from an identifiable collection of languages. And the second result, which is technically much easier, is that hallucination detection in the limit is possible for all countable collections of languages if the learner receives negative examples in the form of strings that live outside the target language K. So for the second result, we need some more from the adversary. The adversary does not merely give us positive examples. The adversary also needs to give us negative examples. It needs to tell us which elements of the domain are not in K. Okay, and now I will just give you a sense of one part of the proof. So for the first result, we said that hallucination detection is possible if and only if the collection is identifiable. So let's see how we go from hallucination detection to identification. Now, similar as before, for each round t, we will denote by S sub t the set of elements that are enumerated by the adversary up to this time step. And we will also denote by L sub t the first t languages that are consistent with this set of inputs. So what the learner does to get identification is the following. Assuming that we have access to this hallucination detection algorithm, we run T copies of it, and every copy is equipped with a different language from L sub T. So the first copy is equipped with a G being the first language from L sub T. The second copy is equipped with G being the second algorithm from L sub T, and so on and so forth. And now, what the identifier does is that it spits out the index of the first language G, for which this binary signal that the previous step returned is 1. And recall that this binary signal being 1 means that this language is a subset. This LLM is a subset of K. So again, like at a high level, what happens is that we have this black box algorithm that does hallucination detection in the limit. We instantiate it with different test sort of LLM sets, and then we return the index of the first set that we are testing, for which the guess of the hallucination detector is 1. Okay, and it turns out that this is sufficient to achieve identification in the limit. The other direction of the result is easier to see. That identification implies hallucination detection, but yeah, I won't have time to get into it. So maybe in the next couple of minutes, let me wrap up with a quick summary on future directions. So language identification started from the 60s. It had a lot of influence both in computer science and linguistics. And now, more recently, generation in the limit has led to various theoretical models and has received attention. And there are various interesting directions that I didn't have time to get into. For example, one such direction is what happens when we have a noise input in the adversarial stream. Another direction that is interesting to study is like how does feedback help in this process? And like throughout this talk, all the notions of breadth and hallucination detection ideas that I mentioned are a bit binary in the sense that the algorithm either has them or it does not. It would be very nice to study more fine-grained notions of them, and there has been some work already trying to do that. Something that none of the previous works on generation have done is relax the validity requirement, and instead of asking that whatever the algorithm outputs is a subset of K, for example, it could ask for maybe sometimes the algorithm makes mistakes, but at least like the times in which the algorithm makes a mistake have to be very sparse. Even if they're infinite, they have to have some small measure that's going to 0. Another thing that has not received too much attention is some type of statistical setting. So it would be interesting to translate these ideas and these models to to settings that have more statistical flavors. And lastly, there has been some study for what happens with generation for uncountable collections of languages. And one interesting result is that generation is not closed under finite unions when we look at uncountable collections. So it could be the case that one collection L1 is generatable in the limit, another collection L2 is also generatable in the limit. But when we take their union, this new collection might not be generatable in the limit. So there are interesting phenomena that show up here. So yeah, thank you very much for your attention, and I would be happy to take any questions you might have.